Hi, Chris. Hi, Gigi. How are you?
Hey, Professor.
Hi, Josh. Hope you're doing good. We'll start in a few minutes. Just check out your assignments and your notes for this week. Let me get five and six. Let's move 6. Okay, so we are going to work on probability today. And so make sure we download the notes and the assignments. And I'll share screen shortly. So I did some grading. I saw that some of you also just submitted some work again. I'll go ahead and update that this week. And so if you have anything outstanding, make sure you get those into me, okay? Okay, so let's share screen. Sorry, just got off a class. Came in real quick trying to start this class. All right, so we are going to cover chapter 9 in about a minute. So check out, we're going to do the assignment together. And then this is the fun chapter. We'll look at probability. Okay, so we'll go ahead and get started. This week is chapter 9, and this is on probability. We are going to look at the reasoning for a certain event that could occur. There's some uncertainty. So probability is just a way for us to look at an event as the ratio of the number would be the favorable of the outcome. The notes give you a little bit of background. So start with Pascal, then go into Laplace. So we're going to talk about some of the theory. And we are going to look at some of the probability in, games and cards, and then how we would apply that into the real world. So as you look at your Canvas, the module for this week is Unit 6. There is some resources on how to do matrices. We're going to come back to matrix when we start doing a little bit of graph. So I'll expand on this, but I put some links there for you in some tutorial. There's also some resources on game paradox, like Monty Hall, deal or no deal. So now when you start looking at like lottery tickets, the contest that they give out, things like that, you can determine the probability of winning based on the choice that you make. Okay. So in this week, we are going to look at what would be equal likely as the outcome and how we were able to yield some possibility in the outcome. So here it starts with talking about things in real world that we would assume the outcomes would be equal likely. And coming back from the sets and the subsets from earlier in the semester, we would say that an event is a subset of a finite sample of space. So we would have a group of objects, and based on that objects, we would determine how likely something can occur, an event can occur. And in this chapter, we also will apply inclusion and exclusion principle. And in here, touching back from when we talked about inclusion and exclusion, we would have a union of possibly two types of events. And in that, we would then look at the sample space of certain event can occur. We would include those and then exclude the intersection of those events. So let's start with dice. And a dice is easy to simulate probability in that your standard dice would only have 6 faces. You would have a face that would have 1 and then all the way through 6. Now, if you have 2 dice or 2 die, that will be a pair. And you see this in like, casinos, or if you ever play with dice, you would see that each dice would be only 6 faces. So therefore, you have 2 dice, you would have 12 faces to work with. But wait, we then have 2 choices, 2 consecutive choices in a set. So here is where we would apply the knowledge that we had previously when we talked about, the combination in combinatorics and permutation, in that when you're looking at a pair of dice, since each has 6 faces, 1 for the white and 1 for the black, then we would then apply the product rule. So the sample space, which is your cardinality of the 2 dice, would be 36 tosses. Okay, so you would take the 6, multiply it by the 6, because each dice have 6 faces, then you would have 36 possible tosses. Okay. Now, let's say that if we wanted to calculate the probability of a certain event that would occur, let's say that I wanted to throw the dice where it would total up to be 6. I would know that the first one can be a 1, the first dice can be a 1, and the second dice can be a 5. That's going to give me a total of 6. The second one can be a 2, or the first one can be a 2, and the second one can be a 4. That also gives me a 6. I can have a 3 and a 3. That also gives me a 6. I can have a 4 and a 2. That should also give me a 6. And a 5 and a 1. That's going to give me a 6. So I know that there are 5 possible ways where I can get a total of 6 out of the 2 dice. So in that, the probability would be that we would have 5 divided by 36, because there are 5 ways I can get a total of 6 out of our sample space, which is the number of faces on each dice, multiply the number of faces on another dice. So that would give me 5 over 36. Okay. But then what if I wanted to get a total of 9 instead of a total of 6? Well, then I can look at the possibility in that. I can have one dice that has a 3, the other is 6. I can have another dice that has a 4, and the second one is a 5. The first one can be a 5, the other one is a 4, and the first one is a 6, and that will be the second will be a 3. So there will be 4 ways that the 2 dice can result in the 9. And as you notice, right, and if you start looking in pattern, you're going to see that we sequentially go up for each of the face, and we sequentially go down for the second dice to get a total number, right? Same thing over here. Then also that we would see that the probability as we raise up the total, right, we would have a lower percentage or a lower ratio in that case. So I went from a total of 6 to a 9. 6 gives me 5 out of 36. 36 is the sample space or the total tosses. Now, if I go to the total of 9, I would then have 4 possibility to get a total of 9 out of the 36 toss. So at the casino, if I want to make sure that I can get a total of 9, I would need to make sure that I pay for at least 4 tosses in order for me to at least get one total of 9, right? Because I know that I would have 4 possibility out of 36. That's going to give me a total of 9. And then in the third scenario, we would see that we want to get something that's higher than 8. Not necessarily 8, but bigger than 8. So higher than 8 could be a 9, a 10, 11, and a 12. Why can't we surpass 12? Well, because there are only 6 faces on each dice. And when you add that up, the highest number on each dice is a 6. So a 6 plus a 6 is a 12. So anything higher than 8 could be a 9, a 10, an 11, and a 12. So then we have to break it down. So in order to get a sum of 9, we already found that in the last one, we know that there will be 4 out of 36. But what if I wanted to get a 10? I can get a 4 and a 6, a 5 and a 5, and a 6 and a 4 for a total of 10. So there would be 3 ways out of 36 tosses to get a total of 10. Then on the next one, a total of 11, we would have 2 ways. I can either get a 5 and a 6 and a 6 and a 5. And so as you notice that we went from 9, which is 4, to a total of 10, which is only 3, and then to a total of 11, that will be 2. So as you increase the sum, you would see that your possibility becomes less. And then I can only get a pair of 6, which is 1 way to give me a sum of 12. Okay. So dice would be a good simulation for what we'll see with possibility or probability. So once I have 9, 10, 11, and 12 for the sum as the number of ways for each of those, then I can add them up. So I would take the 4 for the sum of 9, the 3 for the sum of 10, the 2 for the sum of 11, the 1 for the sum of 12, and I total them up, which gives me 10 out of 36. And you can reduce that down to a smaller ratio where you would take 10 divided by 2, 36 divided by 2, you would get 5 over 18. So I know that out of the 18 tosses, 5 out of those might be, right, 9 or 10 or 11 or 12. Okay. So we just logically set up the possibility for each of those, and then we sum them up and divide it by our sample space, which is the maximum number of tosses we would have based on our dice. Okay, any question with this? Okay. So we're not done. What if we want to get 7 or 11, right? You know that there are some games that if with dice that we can get a 7 or 11 and we win. So we would look at the sum of 11, which we know that there will be 2 ways from the prior exercise. And we also can look at the sum of 7. Well, I know that there's 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. That will give me a total of 7. So if you count this up, that will be 6 ways to get a sum of 7. So to get a 7 or an 11, we wanted to look at the probability in that. We would have a 2 from the 11 sum and 6 ways from the 7 sum, and we add that up, which gives us 8 out of 36, or reduced down to 2 out of 9. Okay, so this ratio represents the probability for that outcome to get 7 or 11 in the dice game. Now, what if I need to roll a pair? Okay, so there's a pair of 1, a pair of 2, a pair of 3, a pair of 4, a pair of 5, and a pair of 6. So that would be 6 ways to get pairs. And we would take that 6, we would divide it by 36, and that will be our ratio, okay, for getting at least one pair. So 1 out of 6 will be a pair. So if I wanted to get a pair, I just have to have at least 6 tosses, right? To get at least one pair. Okay. Then what if I wanted to just to get a number 3 or a number 4, right? So I can get a number 3 or 4 and 4. So I know that a pair of 3 and a pair of 4, that will be 2 ways. So 2 out of 36 or 1 over 18. And then snake eyes is the nickname for a pair of 1. So that will be only one pair because there's only one exact pair in the pair of dice for 1, a 1 and a 1. Okay. All right, so you got a little bit of preview in what we're going to be doing. So let's start doing our assignment. So when you first start approaching a probability problem, you need to first calculate the sample space. So the sample space is the maximum number, right, that would be for that group of values or objects. So since we have a pair of dice, like we talked about before, there are 6 numbers in the dice 1 through 6. So we would take the first dice, which is 6. Since we have a pair, we would then multiply it by another 6 for the second dice, which gives us the sample space of 36. So here my explanation is that each dice has 6 faces. Using a pair of dice would consist of 36 faces, which is the sample space. So cardinality of the first dice is 6. Second cardinality is another 6. You multiply that, you get 36. So I'm using a table very similar to what you've seen in the notes. And now we're going to have the pair of dice, red and black. So if we want to yield 7, like what you've seen in the notes, I would start with the red going up and the black going down. Okay, so I would start with the 1 on the red. You can fill that in. So the first combination I would have is a 1 and a 6. Then for the second combination, I would then have a 2 and a 5, right? That total up to be 7. For the third combination, I would do a 3 and a 4. And then for the next combination, I would do a 4 and a 3. And then the fifth combination, I would have a 5 and a 2. And then on the last combination, I would have a 6 and a 1. And that would be the total number of variations. I can get a 7 in a pair of dice. So what it is, it's probability. I can have 6 ways to roll the dice to yield a 7. Okay, so first what you want to do is to find the sample space. The second step is to look at the number of combinations to yield a certain event. Then you would take the number of combinations and you divide it by the sample space. Then you would get your probability. So that means that I can take the 6 divided by 36, which is my sample space, which gives me 6/36. You can reduce that down by dividing the top and the bottom by 6, which gives me 1/6 tosses. That's going to be a sum of 7. And if we put it into the calculator, and it doesn't matter if you leave it as a ratio, non-reduced or reduced, that's fine. Okay. But if we take the division, we would then have 0.6667. And if you know how to convert that to percentage, that will give me a little bit under 17% of getting a total of 7 in both dice. Using 2 dices, I should say. Okay. So that is very similar to what you have in the notes. Any question with this? So as you can see, we can use this table to really find our combo. It's easier to really type it out. And so you can just count it up, right? I have 7 combo. And so that will, or 6 combo, that will be 6/36. Okay. Then we would then look at the second requirement for the event. Okay. Let me see if I can move this up a little bit. Hold on 1 second. I don't know why it drops it on the next page there. Okay. So as we go to the next scenario, which is number 3, it asks you to find the probability of rolling a sum that is less than 7. Okay, so we already found 7, but we wanted to see the probability of less than 7 sum. So then that means that we would have a sum of 6, 5, 4, 3, and 2. Not a 1 because we have to use 2 dice, right? And the lowest number is 1 on a dice. So that would be 2, not a 1, because there's no 0 phase on a dice. So then we would start putting together the first combo. I mean, the set of combinations for the first sum, which is a 6. So I would have a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, and a 5 and a 1. And that gives me 5 combination to get a sum of 6. So I would take that 5 and I would divide it by 36, which is the probability. And if you take a 5 divided by 36, you would get 0.13889, which when you multiply it by 100 gives you 13.889%. So you can leave it like this. You don't have to put it into decimal or convert it to percentage. So we see that from going from 7 to 6, you would find that it would be less, right? Okay, in the combinations. Then we would start looking at the combinations of sum of 5. And you can type it out. You don't have to put it in the table, but if you like to use the table, you can copy and paste it and then fill out the combo. So to get a sum of 5, I would have a 1 and a 4, a 2 and a 3, a 3 and a 2, a 4 and a 1, which give me 4 combinations. And we see the pattern, right? From 6 to 5 to 4. Then we would take the 4 divided by 36, which gives us the probability. And we can reduce that down to 1/9 by dividing the numerator and the denominator by 4. So that will be 1/9, or 4/36. So after the combination for the 5, I would then find the combination for the 4, and you guessed it, it will be 3, because it's reducing in the sum. We are going to reduce in the number of combinations. So what are the combinations? I would have the 1 and the 3, the 2 and the 2, and the 3 and a 1, right? Those are the numbers that would add up to be total to 4. So that means that my probability is 3/36. Or if we simplify that ratio, it would come down to be 1/12. And then I'm not done. I still got 2 more to go. So then I would need to find the probability of the next one, which is 3. So then I would refer to the combination. So my combination for the sum of 3 is 1 and 2 and 2 and 1. That's easy. That gives me 2 combinations. I would take again that combination and divide it by 36, which gives me the probability. That will be 2/36, or if we simplify that by dividing by 2 on the top and the bottom, which gives us 1/18. And then the last one is that we have to find a combination that yields the sum of 2. And we know that there's only one face that has a 1 on each die. So 1 and a 1 is going to be the pair. That's going to be a sum of 2. So one combination for the sum of 2. And that would give us 1/36. So after you have each of the combination for each sum, you have the combination for each sum, then you're going to add them up. We're going to take the 5 plus the 4 plus the 3 plus the 2 plus the 1, because the question asked us to be less than 7. So that gives us a total of 15. There are 15 combinations that would give us the sum that is less than 7. So then we would take that 15 and we'll divide it by 36, which is the ratio for the probability. So your probability for dices that would give us the dice toss result that would give us less than 7 as a sum is 15/36, or 5/13. In that, if we take the top and the bottom divided by 3, we would reduce that down to 5/13. And if you want to calculate that into the percentage, you would see that there will be 41.67% to get less than 7 as a sum. Okay, so 5/13 tosses would give us less than 7 as a sum. So these exercises are pretty simple, right? We just got to go through the steps where we would find the sample space. Then we would examine the combinations that would meet the event requirement. Then we would take that combination divided by the sample space, and that will give us the ratio for the probability. Now, why is this important? You say, I don't care about dice game and things like that, right? But you will have to find probability of certain outcome in computer science, in programming. Let's say that you want to predict stock prices, or if you want to look at, you want to predict sales, right? Probability for a certain store, or user habits, or all of these trends and things that you see. That is really looking at something that would be likely happening, or an event that could likely occur. So when you're, how things are being advertised to you on the browser, right? Like if you continuously search for something, what it's doing is taking that data, and the algorithm that they have is that, if you search for it more than a certain amount of time, so it's looking at the percentage, right? Of that type of search, and then it's using that toward the algorithm, and that's how they're going to be able to feed it. So let's say if I'm looking for running shoes, and I would do that over a number of time, in a period of time, let's say a month, right? If I search for it 8 times, and then that will be compared to all my searches. So then how likely of that I would be able to buy shoes? So they would use an algorithm to really predict, right, my purchase pattern based on my searches. So a lot of these things we already been using. It's just, you have to look at how all of this stuff would apply to programming, and that would apply to the real world. Okay. And businesses do this, right? Our government does it, and so on. Okay, so for the next question, it asks you, what is the probability of rolling the dice with the result of the snake eye, 1 on each dice? And we already saw that in the exercise. There's only one pair of 1 each, right? So that's going to give you 1/36, which is roughly less than 3%. So if you calculate that out to decimal and then multiply it by 100, you get a percentage. Okay, so 1/36 is going to be a pair of 1s. So for exam and quiz in this class, likely you will get these type of questions on the next quiz and then your final exam. Okay, it will ask you for a certain probability of an event given certain scenario. And you can elevate this by looking at some of the game show paradox, right? Like if an individual, if a contestant picked a certain door, let's say door 1, door 2, door 3, and but they reveal one of the door, okay, how likely if that person's going to win a car or something behind that door? So I posted the paradox information, so if you're curious, right? So from here on out, when you're watching game show, you can predict what will be the outcome when a certain person make a certain choice. And so now I think a lot of the things that we see in programming and in development is that we started to see more intuitive way to make a decision, where it would present you instead of a very large set of decisions, but it's going to narrow down to more of a appropriate or a valid set of decisions. Okay, by implementing the algorithm. Okay, so for the next question, it's a little harder. This one For number 5, it asks you to determine the probability of the red dice has a higher value than the black dice. So to simulate it, I would then look at the roll. So if the combo, let's say, so if I have the red dice as a 1, the black dice cannot be a 0, so I cannot count it. Okay, because red has to be higher. So 1 has to be higher than the other. So for the second one, I can get a 2 on red and 1 on the black. So that's 1. Because there's only one way for that. If I get a 2 on the red, the only other way that I would get it lower, it would be a 1. Then for the next roll, if I get a 3 on the red, I can have a 1 or a 2 on the black. So there are 2 ways to get something lower. So 2 there, 2 variations. Then on the next roll, if I get a 4 on the black, I can get a 1 or a 2 or a 3. So that will be three variations to get something lower if I get a 4 on the red. Then for the next row, if I get a 5, I can get 1, 2, 3, 4 on the black. And that will be 4 variations, right, to get something lower on the black if I get a 5 on the red. And as you can see, we do see a pattern, right? And then the last roll is 6. If I get a 6, if I roll a 6, then I can get 1, 2, 3, and 4 and 5. So I have 5 variations, okay, to if I roll a 6 on a red to get something lower on the black. So once I have all of those combinations or variations, I would then add them up. So I would start with the first row, that's nothing, right? Second row, third, 4, 5, and 6. So I add them up and I would get 15. Then I would take that 15 and I would divide it by my sample space, which is 36 for 2 dice. And if I want, I can reduce that down. So 15 over 36 rolls or 5 over 12, which gives you a little under 42%. Okay, any question with this? Let me move this up a little bit. Okay, so that one's not too bad, right? Number 5, you just have to think about if I get a certain value on one dice, what could be the other dice that would be lower? And that's how we come up with these variations. And then we would total up our combo and then take that and divide it by 36. So for question 6, it says, what is the probability of rolling even number on both dice? So we can say that if both dice come up even, the sum will be even. Okay, so if I have a 2 and a 2, that's a 4, which is an even number. I should say even number right here so you don't get confused. And then, but if I do have an odd in the mix, it's going to give me an odd, right? Like a 2 and a 1 is going to be a 3, so no. So if they're both even, then they're going to give us a sum that's even. And we know how to find sum already. Okay. So then we would start with a 4. So I can have a 2 and a 2, right? And then a 6, an 8, a 10, and a 12. So that means that we have to look for some that will be 2, I'm sorry. Yeah. So it would be 4, 6, 8, 10, and 12. Why can't I use a 2? Because the 2 won't fall into this requirement. Because in order to get a sum of 2, I have to get both ones, and ones is they're odd, so can't be that, right? So I have to start with a sum of 4 and up. So to do a sum of 4, I have here I have a 2 and a 2, right? And that will only be the sum of 4. And then I can start looking at the sum of 6. I have a 2 and a 4. Okay, and a 4 and a 2. Or you can do it like the way I did it. I just go from, 4, 6, 8, 10, 12, and so on, and I just count it up. But keep in mind that you do have combinations, right, for a certain sum. And then we're going to go to 8 next. So 2 and a 6. And then a 4 and a 4. And then a 6 and a 2. And that's an 8 sum. Then we would do a sum of 10. So I can have a 4 and a 6. A 6 and a 4. And I cannot count the 5s because 5 is an odd number, right? In order to get a 10, I have to get 2 5s. So no, I cannot count that. So I'm only going to include even on number on both dice. So a 4 and a 6 and a 6 and a 4. So that's going to be my 10. And then lastly, I'm going to do the 12, which is a 6 and a 6. Okay. So when you count this up, you would have 9. 9 ways to get both dice as even number. And what's the probability in that? You would have 9 over 36. Or if we reduce that down, that will be 1 over 4 or 25%. So the way that I set this up in the table, it's pretty easy, right? You would use the 2s, and then you go up to the 4s, and then you go up to the 6, and then the same thing from the bottom, right? Or you can start with the 6 and then go downwards. Whichever is easy for you to really see how the combinations are. Okay. And on the bottom, I just do 2, 4, 6, 2, 4, 6, so I can track the numbers. Yeah. So there you would have the probability of both evens. Now, if you get a question where it asks for odds, then you can think about what would sum up to be odd, right? Two, well, two odd values is going to give you an odd. So if they're both need to be odd, so you would have a sum as odd value, right? Actually, I take that back. I retract that because a 1 and a 1 is a 2. So a 1 is an even and then 1 is an odd. It's going to give you a sum of odd. Okay. So the whole point in all of these exercises to show you the stages on how you would solve it. Sample space, combination, ratio. Okay, those are the three things. That's how you achieve that. Okay, any questions on the dice example or exercises? Okay, next we're going to talk about playing cards. And some of you might not be familiar with cards because if you don't play cards, you wouldn't know. So a single deck of cards, taking out the joker, okay, because they sometimes put in the joker. We don't count the joker, we only count the suits. So there are 4 suits and 2 color. Okay, the spade and the clubs are black. The diamond and the hearts are red. In each suit, you would have 1 through 10. So you would have an ace, which is 1, and then you have 2, 3, 4, 5, 6, 7, 8, 9, 10. And then your face cards are jack, queen, and king. Now, in some games, they would count the face card as an ace, but for the sake of our exercise, we would only use the face cards as jack, queen, and king. So there are 4 suits, and then there are these many cards in each suit. Now you will see why certain casino uses a single deck, a double deck, or a triple deck if you ever gamble at the table. Right? I'm not a gambler. I have played games before at the casino, or have you seen it on TV or been in the casino, right? So some casino would try to increase the odd for winning by using certain decks, like certain number of decks, and we're going to see why. Okay. All right, so first let's take a look at the sample space of a deck of cards. And here it tells you 52. How did I come up with 52? So if you count up each suit, the number of cards in each suit, I have 3 face cards, right? And I have this many, right, number cards. And I multiply it by 4. So I have 9 here, and then I have a 3. So 9 plus 3 is 12. So each suit have 12 cards, right? I'm sorry, 13 cards. And then if I take 13 cards, multiply it by 4, which gives me 52. Okay. So so I can say 13 cards per suit, and there are 4 suits. So I would take, right, so my sample space is 13 times 4, which is 52. So now for the next question, it asks me, what is the probability for B if the card is a face card, jack, queen, and king? There are 3 face cards per suit. and then there are 4 suits. So if you take 3 times 4, you would get 12 face cards. Okay. So you can say 3 face card per suit. And then there are 4 suits. So that is going to be 3 times 4, which gives you 12 face cards. 4 jacks, 4 queens, and 4 kings in the deck. So that means that we would have 12 over 52 that will be face cards. Okay. So 12 over 52, and we can reduce that down to 3 over 13. Any questions? Okay, so now we're going to look at the next scenario and we're going to do the assignment together. It's not too long. So what if I want cards that's black, right? We know that there is red and black, two suits that are black and 2 suits that are red. So 50% of the cards are black and 50% are red. So that means that half of the cards are black and then the other half is red. So that's going to be 1 over 2. What if I wanted to draw a card that's going to be a heart card? Okay. We know that there is a suit that is a heart. And so that means that there are 13 hearts in that suit. Okay. So that will be 13 over 52. What if I want to draw a queen? And that could be a king or a jack, same, right? What if I want to draw a queen? There are 4 suits and each suit has 1 queen. So 4 queens. Okay. So I would take 4 divided by 52, which gives me the simplified ratio as 1 over 13. Then what if I wanted to draw number cards, but not using the ace, between 2 through 10? Okay. So we know that from 2 through 10, that will be 9. And we would take 9 times 4, which gives you 36 cards. And 36 over 52, or reduced down to 9 over 13. And so for somebody that's guessing cards, right, they have to really quickly calculate the probability based on the sample space, which is the number of cards that's being shuffled, right? And card guessing is illegal at the casino. But if you ever visit some of the casino, they always show like the cheat type of device that people come up with, right, for counting cards and things like that. And mathematically, we can always find, right, the outcome by using the calculation for probability. So on the last one, G, a card that is ace of spade. Well, there's only 1 ace of spade, just like there's only 1 ace of diamond or heart or clubs, right? There's only 1 ace per suit. So 1 out of 52. Okay. So there's only 1 ace of spade, but if it asks for ace in general, then we would have 4, right? 4 ace, 1 per suit. Okay. And then since we didn't include the joker in our deck, because if you include joker, your deck is larger. So that will be 0. Okay. So let's do the next one. Number 7. If a single card is drawn in a standard deck of 52 cards, what is the probability of each of these events? We already talked about the queen. So if the card is a queen, there are 4 queens in a deck. There's a queen of diamonds, a queen of hearts, the queen of spades, and a queen of clubs. So you have 4 queens in a deck, just like how you have 4 kings or 4 jacks. So 4 out of 52. And you can reduce that down further, or you can put it down to decimal if you want. So to draw any queen, right, that will be about close to 8%. Okay. Now, in question 7b, it asks you for a card that is red, a red face card, not just red, right? Red face card. So there are 2 suits that is red, which is heart and diamond. Okay. So if you're looking at each of the suit, the face card for each suit is Jack, Queen, and King. Okay. That's going to be the face card. And these are the suits that are red. So if you count them up, there are 6 face cards that are red. And so you would have 6 over 52, which is about 11.5% to get a red face card in a deck. Because in some games, we would say some games suits matter, right? Blackjack is not one of them. But when you're doing like poker or, you know, a certain type of games, card games, and, you know, programmers build these card games online, whether it's for a gambling website or not, or just for fun, right? In your phone or on your computer, you can look at all these different type of card games. Yeah, I like to include card games in my project because a lot of people know how to play card games. So it teaches you how to take the concept and then apply it in programming. But having discrete structured knowledge is very important because you start to see the probability. So when you program, you have to really include this. Okay. When you remove the card from the deck, right? As they draw that card, it has to reduce from the deck. And then, you know, and so if they draw the cards, you have to weight in the probability in that. Okay, next question, 7C. Cards have the same suit. So I know that each suit have 13 cards. I have 1 through 10, and then the phase cards. So 13. So if the cards have the same suits, meaning that I can get a 2 of clubs and a 5 of clubs, right? So the probability in that, I would have 13 out of 52, or about 25%. So if we apply pigeonhole theory, right? When you started drawing cards, you have to draw at least 13 or higher to get you the same suit. Okay. All right. For D, it asks you for an even number such as 2, 4, 6, 8, or 10. And so if you count that, right, 2, 4, 6, 8, 10, there are 5 even numbers in the suit. So that will be 5 out of 13 because there are 13 cards per suit. I should put that here. And if you're looking at even number for all suits, that will be 20 out of 52. because there are 4 suits. And so you take 5 times 4, and then you take 13 times 4, which gives you 52. Okay, so card is another good tool to really illustrate the probability, and because it's commonly used, it's a good way for me to show you how to really look at cards and the probability. And some of you are familiar with some of the games and things like that. So and taking the card concept into programming, some of the simple things can be, it just take a little bit of time or a little bit of effort to really put this in, right? So if you're building out a deck of cards, you can have an array in C++. Okay, and then you have to think about how you would represent, right, the number cards and the face cards. Now, depending on the type of game that you're making it for. So if you're doing a blackjack game, in that the suit doesn't matter. So you have to think about the data type that you're using. Should you use int? Should you use char? Should you use string? And I see that sometimes students, they struggle with that. But if you think about it, if your suit doesn't really matter, does it really matter that you have it in a certain string? Because a queen is a queen in a deck of cards, right? For blackjack, because when you draw a queen, it's equal to 10 points. When you draw a king, it's equal to 10 points. Okay, so some people, they approach it with an integer. Some people, they approach it with a char, okay, for each of the card representation. Okay, so when you address this in your project, you have to think about what data type that you're using, how you're using your container to really disseminate the cards, right? Because when you program it in a game with an interface or not, you have to think about all of these little processes, all of these things that would play into the process. Okay. All right. We'll talk more about the project later. That's just only one of the options. You don't have to do the games. And I think I'm going to include another game in this for this round. So, okay. So let's look at another example before we do the next one. So here is where we're picking out the balls. Okay. We have red and blue. We have 15 red and 10 blue. So we have to think about first, determine the sample space. So I have 15 red and 10 blue. That gives me 25 because I add them up, right? And why am I not multiplying here? Anyone know? Why is it not 15 times 10? No one knows? Just like how the cards is, right? We add up because they're different. And when we're selecting the balls from the container, we are actually, even when we're selecting multiple, right? We have 15 red and 10 blue. So that's your total set size. Your cardinality is only 25. Okay. So we're just adding. No product rule here. Okay. So then we have to determine the probability of drawing a red. So if I wanted to pick out one red ball from the urn. Okay. For number 2, there are 15 red. And so your probability is going to be 15 out of 25. which we can reduce down to 3/5. So I have to pick at least 15, right, out of the urn to get at least one red, at least one, based on pigeonhole. But there are 15 red, so we would just take 15 divided by 25. What if I wanted to get a blue? So if I want to draw blue, then I can take 10, right, which is what we see in the original experiment scenario here, divided by 25, which gives me 2/5. And you can notice that, right, 3/5 plus 2/5 gives you a 1. And if you have taken statistic, right, they also address probability and statistic. So what you would see is that that would be 100%. So I would get the red and the blue combined is going to be one entirety. So they are always going to complement each other. That's important to note because we're going to come back to this in the future chapter and we're going to see the complement of it. Okay. So now if you are taking out individual draw, that was what we would see. A single draw, this is when we do the addition. Okay, 25. But in the next scenario, the next exercise, you would see that you are picking 3 of them at the same time. So in this case, since it is consecutive selections, we are going to do a product. Okay. And it also depends on whether you put them back or not. Right? If we take them out and we remove them from the original group, then it becomes permutation. If we put them back for reselection, it is then combinations. Okay. So going back to the last unit, we talked about choosing. So if we choose 3 out of 15, we simply apply the R permutation or the choosing formula, right? Which gives us how many ways that we can select 3 red. And if we are selecting 2 are red and 1 is blue, so we would then calculate, choose 2 for the red and then 1 for the blue, which is 10. And then we multiply that because we're selecting them together, consecutive choice, so product rule. So that gives you 1,050 ways. So you would take that and then divide it by the sample space, which is a product, right? You see here? That is going to give you the ratio. So let's talk about another scenario. What if we have an urn and we have 15 red and 10 blue? And we are going to take out 3, each drawn, but we are going to put them back as we take them out, right? So then you have 25 to start with because a 15 plus a 10 is 25 choices. And then you are going to raise it to the 3rd power because you are selecting 3 balls. So then you would have 15,625 sequences of 3 balls and then we replace them, we put them back. So then if we wanted to select all 3 that are red, we would then take 15 to the 3rd, which is 3,375. So we would take 15 to the 3rd divided by 25 to the 3rd, which is our ratio, our probability. What if you want to mix them up? What if you wanted to do two red, I'm sorry, yeah, two red and one blue, like what we've seen in the last scenario, in the last exercise. So we would have 3 position for blue, and then there are 10 that will go into this position because there are 10 blues, right? So then you need to have 15 to the second because we're selecting 2 red, which gives you 225 for 2 red. And then only 1 blue, so you multiply it by 10. And then you have to apply the 3 because we have 3 total, right? So which gives us 6,750. Then we would take this and we would divide it by 25 to the third, which gives you the ratio for the probability. So to approach these problems, again, you would go back to sample space, and then you have to think about how you're selecting the objects and whether that object is being replaced or returned into the original group. If it is, then your sample space is tremendously bigger. Okay. And how the requirement for each of the object, then you would then apply the logic in that. Okay, so let's do the next one together. There are 10 balls, and we are going to label 1 through 10 in the bag. And we want to draw a ball that is 8 in a single draw. So we know that there are 10 balls, so that will be 10 possible outcomes. And there's only going to be one that's going to be 8. So 1 out of 10. That one's easy. Okay. So I just needed to pick the 8 ball out of the 10. So the probability to get the 8 ball is 1 out of 10. Now, if I'm given 3 draws and I need to take out number 8, and every time that I take out the ball, I'm going to put it back. Okay. So when you approach this problem, you would say, oh, there are 3 draws. So my exponent is going to be 3 because your cardinality is 10. So you would take that cardinality and raise it to the 3rd power because there are 3 draws, right? So the first step is to determine all possible outcomes. So you would take the cardinality 10, raise it to the 3rd, which gives you 1,000 possible draws, possible outcomes. Now, if we take the 8 out, right? There's only 1 ball that's going to be 8. There's 9 other that's not. Okay. So here is where we apply inclusion and exclusion principle. So we are going to exclude the ones that is not an 8 ball. So which are those? That's going to be 9 to the 3rd, because remember, again, we're doing 3 draws. So if you take 9 raised to the 3rd, you have 729 outcomes that will not be an 8 ball in any draw. And then we would then leave 271. So how did I get this number, 271? I would take 1,000, I subtract 729, which gives me 271. And that leaves 271 outcomes that do not, that contains 8. Okay. So we need to exclude the ones that are not an 8 ball. And that will leave us with the total draws that could be an 8 ball. So that will be 271. And so once you have that, you're not done, then you take the 271 and you divide it by 1,000 because that's the possible draws. So that the possible outcome. So that will be your probability. Any question? So to approach this problem, we would then start with all possible outcomes, right? Take the cardinality and apply the exponent, and that would depend on the number of draws. Then we need to find out what to exclude. And so we would then exclude the ones that's not based on the scenario that's given. And then we would find the difference. So the outcome of the difference is going to be right for our 8 ball. So then we would take that outcome and divide it by your sample space, which is then give you the probability. All right, let's try the next one. Any question on B? And you don't have to put it verbatim, right? I put down the notes so you see exactly how it's calculated. And again, these assignments, all of these notes, the things that we do in class, the lab, they're for you to refer to down the line or in doing class or, you know, for quiz and so on. So as clear as you want it to be. Or if you just want to type the answer, that's up to you. Okay. C. The probability of drawing the ball number 8. We want to pick out the 8 ball and in 3 draws, but we don't put the ball back. Okay, so as we take them out, we're going to remove them completely. So that changes the game, right? This last part. So then we know that there's 3. And so here we would start with 10, take 1 out, multiply it by 9, take 1 out, multiply it by 8. So our sample space is less. It's 720 possible outcomes. So then after you come up with your sample space, right, based on the criteria, then you would go and you would determine what to exclude. Okay. So as we remove one, so if we start with the 10, there are 9 other possibility or 9 other balls that's not an 8. Then you go to 9, there are 8 other balls that are not an 8. And then you go to 8, there are 7 other balls that's not an 8. So you would then need to take 9 times 8 times 7, which gives you 504 possible outcomes that do not include 8 in 3 draws. That we remove the ball each time. So once you come up with the exclusion value, then you find the difference. You would take your sample space, subtract the possible outcome that do not include the criteria, which is the 8 ball. You would have the difference, which is 216 outcomes that include the 8. Then you take that 216 and you divide it by the sample space, which gives you the ratio for the probability, 310. 3 over 10. It's about 30%, 30 something percent, 33. Okay, any question? No question. Okay. So then we're going to look at the next one, D. What if you want to draw the number 9, the 5, and the 2 in any order? And every time that you draw the ball, you're going to put them back. So just like the dice, right, that we did, the exercise on dice that we did earlier, you're going to have to take a look at the combinations of 9, 5, 2. Okay. So I would have a 9, 5, 2, a 9, 2, 5, a 5, 9, 2, a 5, 2, 9, a 2, 5, 9, and a 2, 9, 5. And that will give us 6 combinations for the number 9, 5, 2 in any order. And this is a combination because order does not matter. So that means that our sample space is going to be 1,000 because we are doing 3 draw and we put the balls back. So we calculate that earlier, right here. So that means that it's 1,000 possible outcomes. So you would take the 6, which is the combination that you came up with right now. 6 divided by 1,000, which gives you 3 over 500. That would be 952 in any order. And when we put the ball back. Question on D. What if you're doing the same thing on the next one, on E? You are using 952 in any order in 3 draws, but you don't return the ball. And we already did earlier how we come up with 720, right? Right here for C. So our sample space for having 3 draws and not putting the ball back is 720. And we already came up with 6 combinations to get 952. So you would then take 6 divided by 720, which gives you 1 over 120. So 1 out of 120 draw will give you 952. That's if we don't return the ball to the bag. Questions? Okay. So there you would have the result for question 8. So in the next example, it talks about bytes, and then it goes into coin toss. You can check that out, similar to what we've done. And then I wanted to go into Bayes' theorem now. So for Bayes' theorem, this is a way for us to find the probability if we already know certain other probabilities. And the example the author uses was smoke and fire, right? So if we already know that if there's smoke, there's a possibility that there's fire, okay? And in the game paradox, which is the following example, then what you would see is that if you have 3 doors and there are prices behind each of the door, and if they reveal one of the door, right, you have to take a look at what is known probability already weighing against the unknown probability. Okay, so here it talks a little bit about the game paradox. Okay, so if the car is behind the door A and the host opens one of the door, right, since they both lead to lemons, then in that case, you would then have the correct response if you don't switch. If the car is behind the second door and the host opened the door C, then you should switch. Okay. And similarly, if the car is behind the third door and the host opened the door B, which has the lemon, right, then you should switch. Okay. So 2 out of the 3 is equal likely the case that you should switch. This means that you are more likely to win the car if you switch. Okay. But most people stay. So this leads us to what we would see as conditional probability, that you would have a condition that's applied, right? Like the host reveal the car or not the car behind a certain door. So based on that, you would have some kind of conditions that would apply to likely what would happen in your choice. So we would see that an event can be independent where it would not affect another event, and other events would be dependent. Okay, so an event that will be independent would be an example of that will be tossing a coin, head or tails, right? If I land a head, it does not impact the outcome of the tail. And the next example, it shows you the dependency in that you have a certain number of marbles or ball in the container, and then you would take those out. So some event would be dependent because it's affecting the, it is being affected based on the previous event. Okay. So here, kind of like what we went over, is that you have marbles, red and blue, right? The chances of getting red or blue or both. Okay. So the illustration here shows you that if you have 3 red and 2 blue here, right, that means I have 2 out of 5 that is blue and 3 out of 5 that is red. And then this is also, if we draw 3 red and 1, that's going to change the outcome of the upcoming. Okay. Or if we draw 2 red and 2 blue, that's going to change the outcome of the probability that is subsequent to that. Okay. So the first event impacts the second event. So in here, what we would have is we would have the probability of the intersection of event 1 and 2 is going to be divided by the probability of event 2. And this is what they call a priori. So, Bayes theorem, that would be relate to the conditional probability, and It is a way for us to look at data sets, machine learning, information retrieval, right, in different type of applications and engineering for science. Okay. And then for the Monty Hall paradox, if you're looking at Bayes' theorem, right? When you read the article, it also explains it, but also your text also explains it. Door behind which, the price behind which door. Should you switch or should you not switch? That also depends on what's behind the open door by the host. Okay. And then other example for virus, right? Testing positive or there's no virus. So the next part we're going to talk about is to doing a tree diagram. In the tree diagram, you would have two main parts. You have the branches and the ends. You always want to start with the probability stating on each of the branch. So in this example, I have A, B, and C. Okay. A is 0.5, B is 0.25, and C is 0.25. And they all equal up to 1, right? If you add them up, they're equal to 1. And then from there, I would branch off. So let's say that I'm at location A and my sales is 70%, right? And my sales on blue socks is 70% and my sales on red socks is 30%. So again, when you branch them off again, the subsequent from the main branch is that you also have 1. Okay. So when you go down the branch from one level to the next, you will multiply. So when I go from A here to this right here, so I would take 0.5 times 0.7, which gives me the probability. But if I'm going across the same level branches, I would add them and they are equal to 1, just like how here is 0.5 plus 0.25 plus 0.25, which is 1. And then again here, 7 plus 0.3 is 1. 0.25 plus 0.75 is 1. So what I note here is that you must multiply along the branches when you go down one level to the next level branch. And then you're going to add when they're in the same level. Okay. So with the positive and the negative for the virus test, that's how it's illustrated. Okay. So let's do that one. Okay, and then we'll talk about Markov and we will end the session. It tells you here that you need to create a tree diagram for a TV manufacturing company to determine the probability of the random selection. There are 3 factories, site 1, site 2, and site 3. And site 1 produced 50% of the TVs. Site 2 produced 25% of the TV. And site 3 produced 25% of the TV. At site 1, you have 70% of the TV is LED. And 25% from site 2 is LED. And 25% of the TV produced in site 3 is LED. So we would start with the branches, right? Listing 50, 25, and 25. And then we would go down to the next level branches for each of the site. Site 1, we would have LED as 70% and non-LED as 30%. Site 2, LED is 25%, non-LED is 75%. And then site 3, 25% is LED, 75% is non-LED. So when we draw it, it looks like this. Okay. So you would start with the first level statistic that it gives you is going to be, and you don't have to make it like exactly like I have, right? You can draw the lines. And if you want to use Microsoft Word, you can do insert, shape, and there are your shapes. Okay. But what we want is we want to branch it out. We have the 50% of the TV, all TV that was produced, right? So site 1 produced 50%, site 2 produced 25%, and site 3 produced 25%. So all of these add up to be 100% or 1. Then from the 50%, we know that 70% of the 50% is LED. So then I have a 0.7 for LED and a 0.3 for other. Then in the site 2 of the 25% of the TV, 25% of those are LED. So we branch off to 25, and that leaves us 75% or 0.75. That's 0.75. That's not LED or other. Then we have site 3. They produce 0.25 or 25% of the TV. And of those TV, 25% are LED and 75% of the TVs are other. So for this one, I like for you to draw the illustration of how you would create a branch, right? Or a tree, a probability tree. And then you branch it off. First level, second level. And then you multiply across the levels, and then you add them down the same level. So let me get this moved to the next one. So it's all together. Okay. So then how do you calculate that? So let's assume that they produce 100 TV, just to make it easy. We would say that 35 of the TVs are from site 1, site 2, 6 TVs, and site 3, 6 TVs. Right? So in calculation, how did I get 35 TVs? How did I get this? So here in purple, I said that site 1, we know that we started with 50% of all television. And of those, they produce 70% are LEDs. So we wanted to look at how many, right? What's the percentage of LEDs? So the percentage of the LED production is 0.35. Then it's given to us that for site 2, they produce 25% of all TV, and of those TV, they produce 25% LEDs. So that gives me, right, this decimal. When you multiply, remember we go from here to here, we multiply. We go from here to here, we multiply. Then site 3, we would take the 0.25, which is here, and of those, they produce 25% LED. So then we multiply again. So same as site 2. So let's look at if we have 100 TV, right? We just multiply it by 100, so that would give us 35 LED, 6 LEDs, and 6 LEDs. But if you produce 10,000 TVs, then you just take a 10,000 and then multiply it by the ratio, and you would get the number of LED TVs. Okay. So you can simply leave it as the ratio. You don't have to do the estimate with, the total number of TVs. That's fine. I just want to show you how that can be applied from the ratio. Question. Okay, so the expectation for this question, right? We need to draw the tree diagram for the probability, and then we need to calculate it. All right. Any question on this? So for Markov, and I included some tutorial videos on this too. You can also find a lot of resources online. So a Markov chain is a mathematical system that would provide you with transitions of one state to another state according to the probability. And it's used a model that's known as probabilistic systems, and to determine how likely is an event that could occur based on the dependency of what's present, but not depending on the past. And you see this in the functionality of our everyday life. Every time that you use turnstile, right? Like when you go to an amusement park like Disneyland, where you scan your ticket and it rotates the wheel and let you in, that the transition for the rotation of the wheel, the turnstile wheel, to let you in is based on the scan of the ticket. And we see this in programming, okay? If you have the user input, right, this will occur. If the input is in this condition, this is the outcome. So for the finite state machine, the finite automaton, and we're going to come back to this, right? So this is a model that can be implemented with using your software and your hardware to simulate sequential logic. If this is the state of the machine, right, it's going to impact the next state. So finite state machines can be modeled in a lot of different things, from your AI to your games to language to everything, our everyday life, or some of the machines that we use, like vending machines, turnstile, stuff like that. Okay. So a system where a particular input cost changes to the state that would represent a finite state machine. And does this happen to your computer? Sure. When you're playing a game, right, you score, that changes the state of the character or the scenery or whatnot. Now, for the push coin operator, like laundromats, vending machines, right? And for my olden days, the payphone. So when you enter that, you insert that coin, right? It rotates the wheel and it gives you your snacks or whatever electronics or whatever you're buying at that vending machine. So in that case, when you see here, it was locked. And when the coin is inserted, right, when that's pushed in, it causes, right, the state of the lock to change. It would then unlock and then drop the treats or whatever you're purchasing. So with this, you have two types. There's finite state that would be deterministic. And then there's also finite state that's non-deterministic. And again, I'm giving you a very brief, right, overview on this because in university, they have classes just for finite or state machines. Okay. So when you're looking at deterministic finite automaton, you would then look at what is being recognized or accepted. Okay. And how it accepts it. So the languages that would made up your binary strings in a certain pattern is going to be implemented for that state machines because your computer breaks everything down to binary, right? And how that would be incorporated. So it would change the state of the machine based on that language. And then in the next part, it talk about stochastic process. And so, and if you're interested in this, right, there are books and a lot of resources online that also give you this, but again, in computer science, it will be revisited a few times. So this process entails some values that's changing randomly over time. And it doesn't remember, so it's memoryless. So the probability of a certain occurrence is not dependent on the step that led to the present state. Okay. And this is known as the Markov property. So I had provided some example here. And so if we're looking at random variable, if we create random variable and we put that into the array. And in that, when it begins to exist as a random variable, it does not satisfy the Markov property because there's no state that lead it to the existing of that variable in the container, okay, because it's randomly generated. Okay, there was no occurrence or event that caused that variable to be at that state, except for that it just randomly selected. So now if we're looking at that container as balls, then depending upon the ball, how they are removed, that is going to really create the process for the probability of what, for the balls that's still in the container, right, that's left. So there's dependency there, as you can see. Whether you put the ball back or you don't put the ball back, that changes how the probability will be at the end. Just like the exercise we've been doing. So you've been experimenting with Markov all this time. Okay. So if you replace the ball each time, it creates a process, right? And it changes the probability for the outcome compared to if you don't replace the ball. So let's talk about extra credit, which is the last one. This is optional. It's not required in your assignment, but if you attempt this, when I grade it, I will pick out the ones that solve it correctly and give you extra credit. And this question is about travelers to Hawaii. So if they're doing island hops, so if travelers arrive in the main island, which is Honolulu, right? or Oahu, then they can stay or they can go to other islands. So the options for the other islands are Maui and Kauai. So the scenario is that once they're on the main island, 70% of the tourists is going to go to Maui or plan to go to Maui. 20% is going to go to Kauai, and 10% is going to stay there. Okay, so this is a perfect matrix problem. Then when they get to Maui, 40% is going to stay there, 50% is going to go to Kauai, and 10% return to Oahu. Okay. Then when they're on Kauai, 30% is going to stay there, 30% is going to go to Maui, and 40% go back to the main island. So when you start in the main island, what is the probability, you can put it in percentage, of people that will stay there at the end of the trip? Okay. Or not stay there, would be on Oahu after the 3-day trip, whether they go to Maui and then come back to Oahu, or Kauai and come back to the main island. So solving a problem like this would also work toward plane, train, right? When you're looking at how people use certain transportation and how they connect the routes and where they come back. Okay, so you can predict, right, how they're going to be able to return, or if they go to another location. And this is used for, routing packages and, for travel, for a lot of things. So if you can calculate this, right, you can apply the concept for applications that would use for other scenario. So you can put together the matrix. I need you to provide me with the transitional matrix, right? And if you don't know, you can attempt to watch the video and try. This problem is actually easier than it seemed. And I need a 3-step transitional matrix. Okay. I try to draw it out. I'm not a good artist, but I put the percentage as you can map it. And then we'll talk about graph and all of that down the line. Okay. So if you include your answer for the extra credit, right, when I grade it, I will make a note of it, and then I will add the extra credit. There will be a column for just this grade. And so I just wanted to give you a challenge to see if you rise to it. And even if you attempt it and if it's not quite correct, you can get some partial credit. Okay. So use matrix and then put in the values and see if you can calculate it. Question. Okay, and we will do matrix down the line, so don't worry. Okay, so that's all she wrote for today. I'm going to stop recording.